Look at this beautiful flame. It is formed by thousands of iron particles that are burning together. And I advise you to better not put your hands inside because these particles reach a temperature above 2000 degrees and release a considerable amount of energy. But you probably wonder, why is this so interesting? You may know that storing renewable energy is a major concern for the energy transition. We must find a technology with a sufficient energy density that can be easily and safely stored and transported, and with a minimum impact on the environment. Well, let me present you the metal fuel cycle. The idea is to take advantage of the high volumetric energy of metals to burn them and release this energy. After combustion, the oxidized powder is empty of energy but can be recharged back to its initial state in a reduction process using renewable energy. In this way, the same powder can be used over and over again to store and transport renewable energy in a closed, carbon-free cycle. Nevertheless, producing pure iron particles is costly, and it would be a real advantage to directly work with impure powders. However, these impurities are numerous, and the influence on the combustion process is not yet well understood. There, my research is finding its full meaning. I'm burning iron particles containing various impurities. To do so, I use an electrodynamic levitator able to stabilize one single particle inside the combustion chamber. The latter is then ignited with a laser, and I can follow the whole combustion process using a high-speed camera. But let's dive together into one of my experiments. On your left, a pure iron particle is burning, while that on the right contains 5 mass% of aluminum. As you can observe, while nothing special is visible on the left, a completely different combustion pattern takes place at the surface of the right particle. Among others, the presence of aluminum changes the combustion time, the oxidation degree, or the temperature reached by the particle. Another example is the occurrence of microexplosions, coming from the creation of a gas inside the particle. Our latest studies suggest that hydrogen impurity may be responsible for the gas creation inside the particle, as observed on the left video, while the presence of carbon impurity seems to enhance the intensity of microexplosions, as shown on this beautiful second video. In summary, you can remember that iron powder has a great potential to become a future carbon-free energy carrier. To help companies scale up this technology, universities can bring crucial information about the suited iron feedstocks that can be used, about the burner's design for an optimal combustion, the most interesting applications for the released heat, how and where should we transport the combustion products to reduce them, how long should we store them, and how many combustion reduction cycles per year should we do. You will have understood it. Scaling up iron fuel requires both a complete understanding of the combustion and reduction processes, but also a global vision to drive the development of this technology forward. I would like to thank my funding source, the FNRS, as well as my promoter, Professor Francesco Contino, and I invite you to contact us for any question or collaboration.